In this problem, we have two gliders, A and B, sliding down along cylindrical bars, each bar identified by the unit vector, which is along the axis of the bar, and the locations of the gliders are given, XA, YA, ZA for the glider on the left, and XB, YB, ZB for the glider on the right. We neglect friction in this problem, and our task is to express the tension in the cable in terms of the weights and the direction vectors A and B. We begin with drawing the free body diagram for the left glider. It involves the weight, the force T that acts along the cable line, and the force NA. The important feature of the force NA that it is perpendicular to the cylindrical surface. So if I think about a circle, then the force NA will be in the radial direction, but we are not sure at what location in the radial direction. In other words, in polar coordinates, we know that the force in the radial direction, but we don't know the angle. The equilibrium equation is very easy to write in terms of vectors. And now we can do pretty much the same thing for the right glider. I want to pay your attention that here the vector t and here the vector is minus t. And of course, both represent the tension in the cable. And of course, these two are related by Newton's third law. The equilibrium equation is, again, sum of the forces. And in this case, I use minus t to indicate that I'm adding the force plus minus t. Again, the force NB lives in the plane perpendicular to the gliding direction. So to manipulate these equations, I will first show how to proceed with the equation for the left glider. So here's the equation. What I do, I project the sum along the direction A, which means I take the dot product with A, and then I expand it, and then I observe that the force NA is in the plane perpendicular to A. It means that NA and A are perpendicular to each other. It means their dot product is equal to 0, and therefore I'm left with these two terms. Now I express T as the magnitude of the force T times the unit vector E, and this allows me to write down the expression for the magnitude of T. I can do pretty much the same things with the second equation, and here I multiply by the vector B, expand, observe that NB dotted with B is equal to 0, and therefore I'm left with only two terms. Express the force T in terms of its magnitude and unit vector and obtain the expression for T. So here we have two expressions. Actually, both of them are correct. The reason we ended up with two expressions is quite simple. The problem is somewhat overdetermined. For example, when we look for the coordinates of E, or better to say for the projections of E, we have the information about the points A and B. We have the coordinates of both points. What is clear that those coordinates are not completely independent because the distance between the points A and B is equal to the length of the cable, and also the points A and B are not completely arbitrary because they are located on the bars. So because the problem is overdetermined, we can compute T in two ways. What is important is that if the data are correct, then both expressions will give us exactly the same result. At any rate, let me see how to quantify this. First, I will compute the vector E. The vector E is the unit vector of the vector AB. So what I do, I calculate the vector AB and divide it by its magnitude. The vector AB is calculated by subtracting the coordinates of the point A from the coordinates of the point B. Please look at the numerator. Then I take all the projections, take their squares and sum them, take the square root, that gives me the distance AB or the length of the wire. Now I identify the vectors A in terms of their projections, AX, AY, AZ, BX, BY, BZ. These projections are not completely independent because, of course, A and B are unit vectors. Now I can evaluate the first expression, T minus W dot A, which is minus WA J minus here, dotted with A, E dot A. This gives me this answer, and I can do exactly the same for the second glider and calculate the tension T using the second glider in terms of and calculate the force in terms of the weight WB. Thank you.